In the previous video, we talked about the Bohr model and how electrons are organized in these concentric circles and orbit around the nucleus. We also talked about how electrons can only exist in certain quanta of energy, and they can only jump between these energy levels when a very discrete amount of energy hits it. However, scientists were skeptical about why exactly electrons could only exist in these discrete energy levels. And that's where de Broglie comes in with his explanation. You see, de Broglie hypothesized that electrons traveled as particles, but they also had wave-like properties as well.
But are you a different animal and the same beast?
What the does that mean, Kobe Bryant?
You're welcome.
In fact, all matter has wave-like properties. It's just that we only notice it on very small massed objects like an electron. Take this rocket ship for example. It has a very large mass, yet it still has wave-like properties. There's slight vibrational patterns to it that we can't detect with our own naked eye. Same here with this basketball. It's much smaller than the rocket, and so therefore the vibrational patterns will be a bit bigger, but we still can't detect it with our naked eye. And so therefore, the smaller the particle, the more detectable these wave-like properties are. And so, if we go back to our Bohr model, our electron isn't exactly a particle that moves around in a perfect circle. Instead, it looks something like this, where an electron has a specific wave property to it as it moves in the atom. The electron isn't exactly traveling in the wave pattern that we see here, but instead it has adopted a specific wave function, kind of like it having its own ID. The whole quantized energy part comes from the idea that all of these waves are standing waves with each other. In this diagram, notice how the electron always comes in phase with its wave. That is, the end of the path meets perfectly with the start of it. This is what's known as a standing wave. The electron can only exist as standing waves at discrete energies. Let's say we want to increase the energy of an electron. Then, it must adopt the next available standing wave. If it tried to create a wave in between these standing waves, then the electron's path would not be in phase anymore, and so it would destroy itself. In the past few moments, we've seen the Bohr model, where electrons were thought of as particles that moved in discrete energy circles, to now, a wave model, where an electron takes up standing wave functions as they move around the atom. But if you've been noticing, I've been very careful not to say that these electrons move in waves around the nucleus. Quantum mechanics is a bit funky in the sense that we can't exactly detect where an electron is at any given moment, and this is thanks to our good pals Heisenberg and Schrödinger. But what we can do is draw out a map of where the electron is likely to be around the atom. In this example, the shaded areas represent places where there's a 90% chance to find an electron, and the white areas represent places where it is highly unlikely to see an electron. These shaded areas are called orbitals, and stay tuned for the next video where I talk more about shells, subshells, and orbitals.